Today, what our objective is to learn a little bit about the periodic table. So we're going to talk about the history of the periodic table. How did it come about? Who built on the original ones? So we're going to start off talking about a gentleman named Stanislaw, I think, Canizario. Stanislaw Canizario. In September of 1860, at the First International Congress of Chemists, Canizario presented a convincing method for accurately measuring the mass of an atom. Well, what did that have to do with anything? Okay? What did that have to do with anything? The mass of an atom. This allowed chemists to agree on a standard value for the atomic mass. And it initiated a search for the relationships between the atomic mass and other properties of elements. So now we can agree. Okay? Now the chemists can agree on a standard value for atomic mass. So, the big hunt, are there relationships between this atomic mass and other properties of the elements? Well, a man named Mendeleev. Look at that guy. A man named Mendeleev. Dmitri Mendeleev. Mendeleev heard about the new atomic masses, and he decided to include these new values in a chemistry textbook that he was the author of. Mendeleev hoped to organize the elements based on their properties. He placed a name of each known element on a card with the atomic mass and other physical and chemical properties. He then arranged the cards according to these various properties and tried to find any pattern in the properties. So he just simply wrote their names on cards. I imagine it's something like a note card. Okay? Just wrote their name on separate cards and tried to arrange them and say, okay, is there anything here? Is there a pattern with these elements? Well, Mendeleev noticed that when the elements were arranged in order of increasing atomic mass, certain similarities in their chemical properties appeared at a regular interval. A repeating pattern like this is called a periodic pattern. Okay? Can anybody think of something that is periodic that we deal with daily? Huh? The schedule of periods? Okay. Absolutely. Unless we have a delay, then it gets a little messed up, right? What day is today? I know this is a tough one. Tuesday. 7 days from now, it's going to be Tuesday. And 7 days from then, it's going to be Tuesday. And then 7 days from then, it's going to be Tuesday. So our calendar is a repeating pattern. Not only with days, but how about years? Okay? 12 months from now, it's going to be September. All right? So, we have repeating patterns we deal with every day. Well, Mendeleev saw a repeating pattern with these elements, in that certain properties repeated every so often. So he put those elements together, and he said that he had a periodic table of elements. Here is a picture of Mendeleev's periodic table of elements. It looks somewhat different than your periodic table, doesn't it? Somewhat different. This is an early version. But what I want you to notice about Mendeleev's version here, okay, and we're going to talk about that here in a second. I want you to look at this right here. There's a 45 with a question mark. There's a couple more question marks, 68, 70. Okay, there's a part right here that's really important. Right there. 128, 127. And notice that he put a question mark after 128 because he was arranging everything based on the mass, the atomic mass, right? Well, that one didn't match up. He said for some reason, and I don't know why yet, for some reason, this element, tellurium, this element has similar properties to all of these guys, but the mass doesn't follow in order. So he says, what I'm going to do is I'm going to flop them because I'm going to match up all those properties that they have together. Okay? Look at here, too. Something else to notice. He left some blank spaces in his table. He left some blank spaces in his table also. Now, why does that have any significance? Well, let me switch to my next slide here. So Mendeleev put iodine and tellurium out of order. He also left several empty spaces, and he said that the properties of elements will fill these empty spaces. So he said, the empty spaces are elements that we have not discovered yet. We've not discovered these elements yet. And he predicted what kind of properties those elements would have when they were discovered. Well, like any other scientists, the chemists back then, they were sitting there saying, well, you're wrong, Mendeleev, because we have all the elements. Okay? This can't be what is going on because all of the elements have been discovered. There are no more elements. Okay? So some of the people thought, you know, hey, this Mendeleev guy's a quack. We've got all the elements. Okay, the table's not good. Then all of a sudden, what happened is somebody discovered another element. And guess what? When they discovered that element, it had the properties that Mendeleev said it was going to have. So then they said, wait a second here. Maybe this Mendeleev guy's got something. Okay, maybe he's got something. So that's how he was credited with discovering the periodic table, because more and more elements were being discovered, and they were saying, hey, you know, Mendeleev was right on. He was right on. Okay? Now, just to show you an example of this, on the left side here, EKA silicon. This is what Mendeleev predicted in 1871. He said that ecoskeleton, or ecosilicone, will have an atomic mass of 72. It'll have a very, very high melting point. Its density will be around 5.5 grams per centimeter. It'll be dark gray, okay? And when paired with oxygen, it'll have a density with 4.7 grams per cubic centimeter. Now, if you come over here, the element germanium was discovered in 1886. That looks to me like 15 years later, after Mendeleev said these are the properties. So 15 years later, atomic mass, was he pretty close? Absolutely. Is that a pretty high melting point? Yep. What about his density? Ballpark. Okay. Was it gray metal? And density when paired with oxygen? So, see how close he was? And he predicted that 15 years before it was actually discovered. That's when, okay, stuff like this led chemists to start to say, hey, Mendeleev, he's on to something. Now, unfortunately for Mendeleev, he wasn't totally correct. He wasn't totally correct. A gentleman by the name of Henry Moseley, who was working with Ernest Rutherford. Now, let's stop and think. Ernest Rutherford, where does he come into play? Have we talked about Ernest Rutherford? Absolutely. What do we associate Ernest Rutherford with? This should be popping in your head. Ernest Rutherford. Yes, Advia. The nuclear atom, what's his experiment? The gold foil experiment. Rutherford, gold foil experiment, the nucleus. So he proposed the nuclear atom. Well, Moseley was working with Rutherford, so he was working and developing this whole idea of the nucleus. Well, he discovered a previously unrecognized pattern. And that pattern was, we got a little shaky and bakey. Okay? That pattern was, he found that the periodic table was arranged in order of increasing number of protons. Increasing order of protons. So Moseley said the periodic table is arranged based on the protons. If you remember, okay, Mendeleev said atomic mass. So Moseley and Mendeleev were slightly different. Moseley said the periodic table is arranged by the atomic number, the number of protons, whereas Mendeleev said it was arranged by the atomic mass. This led us to the periodic law. The periodic law. And that law states that the physical and chemical properties of the elements are periodic functions of their atomic mass. Now I want you to look at your periodic table. Okay? Look at your periodic table. Way back when, Mendeleev put a question mark on his table and said tellurium, iodine. Tellurium, iodine. I'm going to flop them even though they don't line up to their atomic masses. Now, does Mendeleev explain why those two elements were flopped? Or excuse me, check. Does Moseley explain why those two elements are flopped? Does it make sense? Because based on their atomic number, if you follow the order, tellurium is 52, iodine is 53, so they're in the correct order based on atomic number. Are they based on atomic mass? No. So, Moseley is explaining now by this pattern of atomic number of why Mendeleev flipped tellurium and iodine.